Hi everyone, my name is Chendi. I'm a machine learning engineer from Intel. Today I will introduce about running GenAI workloads with Ray on Intel Gaudi Accelerator. Okay, so there will be 3 parts covered in this session. Firstly, I will give an introduction of Intel Gaudi Accelerator. Secondly, I will present how to enable Intel Gaudi on Ray with Ray Core, Ray Train, and Ray Serve. Then we will dig into the details on how Intel Gaudi helps accelerate AI performance, no matter you are doing a training, fine-tuning, or serving with Ray Serve or VLM. So let's start with the introduction of Intel Gaudi. So what is Intel Gaudi? Intel Gaudi AI Accelerator is designed from the ground up for AI training and inference. So there are 3 main subsystems, including the compute units, memory units, and networking. So for the computer design, Gaudi is built with heterogeneous design with MME and the TPC. I think if you look at the page here, the about part said Gen engine, which is MME, and underneath is a TPC. So what is MME? MME is a matrix multiplication engine, which is responsible for all the linear operations, such as fully connected layers or convolution layers. And the TPC is a programmable tensor processor core for nonlinear operations, such as spatial pooling or batch normalization. So the good side is that on the software side, user can also develop their own kernel runs on TPC. And also, we provide a predefined TPC kernels, which is fully optimized with Intel's Gaudi software suite. I will mention later. For the memory design, Gaudi provides SRAM, a TPC local memory, and the HBM device memory. For the network, Gaudi uses Rocky version 2 RDMA, which allows linear scalability, both scale up and scale out. So released in Q3 2024, Intel introduced the Gaudi 3 with the next level of AI performance and the power efficiency. Advancing from the previous Intel Gaudi 2 accelerator, which is 7nm process, the Intel Gaudi 3 accelerator is manufactured in 5nm process, which provides improved area density and power efficiency. So as you can see here, for the computer side, we now have 8 MME compute units and 64 5th generation TPC units. And for the memory, we provide 16 HBM, which provides sum up as 128 gigabytes device memory, which is super large. You can even run a 70 billion model if you quantize this as into 8. And with 96 megabytes SRAM. For the network, we provide sum up as 24 multiplied to 100 gigabits per second network bandwidth. Okay, so now let's talk about the software. So we have this powerful hardware, but it's not NVIDIA, right? So we need to provide a software layer which will help users to enable the efficiency mapping of neural network topologies onto the Gaudi hardware. So on the top, we provide PyTorch bridge, which seamlessly connects module executor codes onto the Gaudi runtime. For the runtime, we provide lazy mode, eager mode, and the torch compile mode, which is really popular this year. And underneath the PyTorch is a graph compiler and a runtime. So this is responsible for the pipelining between MME, TPC, and the DME, all the compute units I just talked about before as the hardware. And also responsible for the execution, scheduling, graph sanitization, node extraction, and the kernel optimization. Then the Intel Gaudi software suite also provides its own communication libraries called HCCL. And underneath are user mode driver and the kernel mode driver. So let's talk about the performance. Some of you may already work with Intel Gaudi 2, which is released 1 year before, and on training and inference workloads. And since Intel Gaudi 3 accelerator comes up with more MME and TPC computing units, large HBM bandwidth and the capacity, so allows Intel Gaudi 3 accelerator to achieve state-of-the-art performance on GenAI training and inference workloads. So chart here compares Intel Gaudi 3 with Intel Gaudi 2. So on the right side, there is a performance improvement for the bottom part is training, the bottom part is inference throughput and inference latency. So we observe that there are 1.75 performance improvement in the training scenarios. Because training are compute intensive, so the increased compute ratio provides immediate performance gain. And the increased HBM bandwidth allows larger computation, and also the larger HBM device memory, which is increased from 96 gigabytes to 128 gigabytes, allows increased batch size, which means before maybe you can do like batch size is 64, 128, now maybe you can do like 526, and allows avoiding recomputation of certain part of the workload and also avoid the model parallel splits. And in the inference part, we also observed a roughly 1.5 improvement. And for the large models like Llama 70 billion or Falcon 180 billion, we see improvement more than 2 times. The larger improvement is also provided by the larger memory capacity, which is available on Intel Gaudi 3. Okay, horizontally, we also could compare the Intel Gaudi 3 with NVIDIA H100. So the data here is collected on March 28th, 2024, NVIDIA's MLPerf dashboard. So we compare token per second and the test time training and observed about 1.25 times up to 1.7 times better performance compared with H100. And on the inference side, compared with H100, we compare with Llama 7 billion model, 70 billion model, and the Falcon 180 billion model, and see average 1.5 times speed up in token per second and a 1.4 times improvement in average power efficiency. Okay, so let's now move on to the next part, which is how to enable Intel Gaudi on Ray. So Intel Gaudi is natively supporting Ray core since Q1 2024. We added a new HPU accelerator manager into the Ray core. If you be part of this keynote this morning, you should probably know what that is. It's a computer resource manager underneath the Ray core. And we also provide the major PRs for HPU support in these slides. If you are interested, you could take a look of that. And enable Intel Gaudi, user only need to specify the HPU resource through Ray init or Ray remote function. It's really simple. And for Ray train, Ray serve, VLM, we also support Intel Gaudi through the Ray core. So here's an example to just enable Intel Gaudi on Ray. As you can see here, the only thing you need to do is just sorry, this is the next page. So this one is just telling you how to bring up the drivers. So we consistently upgrade Gaudi software through the Docker image. Now we released version 1.17, and the 1.18 release is just around the corner. And what you need to do to launch Gaudi container is just to download the latest image and install Ray inside this Docker. Furthermore, we recommend users to also install another 2 optimization packages, which is Optima Habana. This is a Hugging Face transformer optimization kit, and also the Habana AI Deep Speed. Okay, so how to enable Ray with Ray core? So it's pretty simple, which is when you specify the resource you assign to HPU in Ray init. or you use the Ray remote decorator to specify HPU resource for different functions or classes. And for range train, so HPU resources can also be specified in scaling config, and the HCC HECO communication library can be specified to the torch config. Then provide both scaling config and the torch config to the torch trainer. So you will have your model trained on HPU. And you may ask if we also need to also need to do additional work in the train function, because that is the most tricky part, right? The answer is yes, but it's not much. I will explain what need to change to your train code in the later LLM training part. Okay, so for Ray serve, HPU resource can be specified in the serve development deployment decorator. In the inference code, user only need to assign the model to HPU. One additional line highlighted here is the wrapping model in HPU graph. This line actually is optional, but it's a very good way to improve your inference performance by keeping entire model operator execution on HPU instead of having those CPU fallbacks. And the execution in lazy mode with HPU graph will help the HPU to capturing the entire model and replay, so we can reduce additional time to waiting for the model to execute. And Intel Gaudi also provides other easy-to-use optimization wrapper and environment variables, which help to accelerate model during the inference. I will share later. Okay, so we still have like 17 minutes, so I want to put more time for here, which is to dig into the details about how to do training, serving with Intel Gaudi on Ray. Okay, so here is an example for training a Llama model. You can also think it's a fine-tuning a Llama model on Intel Gaudi with Ray Train. So firstly, we import additional package called Optima Habana, which is a Hugging Face Transformer Gaudi optimization kit. Then we also need to import like Gaudi trainer, Gaudi config, and the Gaudi training arguments, and also adapt function called adapt transformers to Gaudi. So that is everything you need to do. Then, as mentioned before, user only need to specify the HPU resource through the scaling config and torch config and provide to the torch trainer. So in the train code, this is the most important part, because other things are just fine, because all the effort we are doing is just to write the training function, right? So for the training function, as you can see, there are only 4 line changes. The first one is we need to call the adapt transformer to Gaudi. So what does this line do? This line actually, because we are providing additional Optima Habana package, which can replace original transformer layer with our Optima Habana layers, and it provides you a better performance. So this is what the adapt transformer to Gaudi do. And secondly, you need to specify training arguments and a Gaudi configuration. You can also use in the default option, but this is to a configuration will help you to control more to your cluster and to your model. And then using the Gaudi trainer to train the Llama model. And the remaining part of the code will stay the same as you write before. So you can see its original tokenizer, its original configuration. You don't need to change that part. And one thing you need to mention is that Ray Train on Intel Gaudi also support DDP and the Gaudi optimized deep speed. And then let's look at this example, which is a LLM serving on Intel Gaudi with Ray. So the process is very similar, can be also do the serving for an LLM model or a regular deep learning model. Firstly, you need to adapt transformers to Gaudi. Secondly, assign the model to HPU, just as you did for assign the model to CUDA as well. And then wrap model in HPU graph. And the first and the third one is optional. Only the second step is necessary. But the first and third step will help you to improve the inference performance. Okay, so we talk a lot about the optimal Habana and the torch bridge optimization. So I also want to wrap in here. When invoke the adapt transformer to Gaudi, as I mentioned before, this is actually replace some known layers from model to model with Gaudi optimization's version of layer. And we are consistently updating the optimal Habana to along with the transformer release. So as you know, last week, Llama 3.2 model just released, right? And along with the Transformer 4.45 release. So there's a new model called M-Llama, multi-model Llama, which is very different from all the previous Llama model. And now it's already been running on HPU. So that is how easy to running any model, any transformer model on HPU. But we're also working with Optimal Habana team to add additional optimization for M-Llama, which is to adding those optimization layer to replace the original transformer layers. And in torch bridge, there is also some code for the user to can control their model process. So I provide some examples here. The first one is wrapping in HPU graph I introduced before, which is to capturing the entire model as a graph. And we capturing and replay, so it will be way faster than before. And the second one is mark step. So mark step is like additional to the wrap in HPU graph, because when we are wrapping a super large model, it might not fit into the device memory, right? So we want to use mark step to split those big graphs into small graphs. And the synchronization is also do the same thing. It's like we can immediately to materialize those lazy tensor, so we don't want to explode our device memory. And the torch bridge also provides a great number of optimized kernels. I put an example here, which is a fused SDPA, and I will provide more examples in our VLM introduction. Okay, so besides all the work we done in ray, train, and ray serve, because VLM is also built upon the ray core, right, for the distribution part. So we also did a lot of work in VLM to support Intel Gaudi. So I believe everyone here is quite familiar with VLM. At least we are familiar with what it is and why it's so popular, because of all these features which can improve the inference performance so much significantly. So for Intel Gaudi, we currently provide a VLM fork project which can run VLM on Gaudi. We also submitting the PR to merging all the modification to the VLM main upstreams. And the Ray is a default multi-process backend in VLM Gaudi project for either tensor parallel or pipeline parallel. And also, all models supported in VLM are supported in VLM Gaudi already. And since the 0.6 VLM was just released a few weeks ago, there may be a small feature gap, but we already sync our code to the v0.6.2. And in enable HPU on VLM, user only need to do is to firstly using the VLM Gaudi project, and then assign the device to the HPU, as I just highlight here. So this is the only thing you should do to enable running inference model on HPU. Okay, so don't be scared of this diagram. I know it looks super complex, but I just want to show out what is the modification we've done in VLM to support HPU. So the diagram here is everything we've been accomplished to support HPU in VLM project. And as you can see, VLM has its own model codes. So it's not like many other projects, which is directly using the transformer codes. VLM has its own model execute folder, which have all the implementation of models, layers in the VLM project. And so because of that, we also need to do additional work to change the original VLM layers so we can provide the fully optimized kernel and the layers in VLM. So this is the part on the top, right button, the blue box, is that, let's say this is a Llama model. So we all are familiar with the Llama model, right? There are the major part is the transformer part in the middle. And what we need to do is we need to write all those kernel in the white box, which we will provide Habana page attention, HPU RMS norm operators, and the HPU rotary embedding function. And also, let's say if this is a Mistral model, then we also provide the fused MOE implementation. And then the other thing I need to mention is the above part, because VLM is very loosely coupled design. So it can provide all types of accelerators because user can provide their own model runners. There are like GPU runner model runners, other accelerator model runners, and as well we provide the Habana model runners. So in the Habana model runner, we implement we are adding a wrapping function to the loading weights, which will initialize the model at the beginning, so we can have a better model quantization function implementation and other things in the loading weights function. And we also provide a model forward wrapper, which, if you remember before, I talked about the wrapping HPU graph function, right? So in the VLM, we're also doing that, but it's already inside the model forward function, so you don't need to worry about that. And we also provide the performance tuning feature adaptation implementations in the input tensor preparations, logic processors, and output sampling. So with above changes, we can have VLM, those brilliant features such as speculative decoding, continuous batching, multi-step scheduling, and also runs on HPU effortless. And for the memory management, I mentioned before, now we have 128 gigabytes device memory. So what does that mean to the model serving in VLM? So as we know that there are three major memory consumption when you inference a model in VLM. Firstly, it's the most important part, which is a KV cache, right? Because this is how VLM showing so significant performance improvement than other project, which is a KV cache. And then the model weights. So let's say if I have a 70 billion model, and I want to just using BF16, which means there will be around 130 gigabytes memory consumption to host this model. And then we also need to provide some device memory for HPU graph compiled IRs. It's very similar to the CUDA graph compiler. And so here, let's say I have this 70 billion model, and I can either use two cards or 4 cards to host this model. But with Gaudi 3, this with 128 gigabytes memory capacity, which means I have at least 40 gigabytes on each card for the KV cache. What does that mean? That means we can host at least 20,000 to 20,000 cache tables with 128 blocks. This is a very big KV cache, so we can host a lot of previous attention KV values, so we don't need to recomputation that. Okay, so what's more? Except for just running VLM or running reserve, there is a possibility that we can combine these two projects together. Because so the light blue part underneath is VLM, and currently it's using the Fast API. But reserve actually it provides a whole different features about Fast API, right? So one solution here is we can also replace Fast API with reserve, so it can be deployed on kube array and doing the any scale scaling. And the example is also provided here, which is contributed by one of my colleagues, and it's on the ray.io. Okay, that's all. Thank you. We have only 3 minutes. Do we have any questions? Yes?
Does it support eager mode execution for PyTorch?
Yes. But sorry, the question is, does it support eager mode in PyTorch? The answer is yes, but we don't recommend that. Yes?
There's a couple APIs that you mentioned that modifies the transformer to support Gaudi. Could you talk a bit more about what's underneath these functions? What they do?
Sorry, can you say that question again?
There were a couple APIs you said we had to add for serving and training.
Yes.
But could you talk a bit more about what those functions do? The modify, adapt transformers function.
Okay. So the question is, what actually the optimal Habana do to optimize the transformer layers? But answer is that it's a bit complex, so I don't think I can share here. But I do provide a link for you. You can just go to the Optimal Habana GitHub. It's very clear there. Yeah.